guys, so let's make some exercises about the transformer. I want to tell you, like for the first 10 minutes, I want to tell you a little bit. So the transformer model, you saw the architecture. It's not hard, but the point is it's been used in a number of tasks. It's also used in some production systems at Google. So the models we write in a Colab, here is a layer, there is a layer, we test a few sizes. When you start doing this on a larger scale, like when you're applying the same model architecture to like 20 different problems, you need to tune it. So things get parameterized. Because you don't want to rewrite, like this is an instance of this model, another, and you have thousands of them and lose control. So the things you do, like we do is like this feed-forward layer. It can be a convolution, it cannot be a convolution. It can be one of many types, right? The attention, what I told you is the basic attention like this. It's attending everything before. But as I hinted, for very long sequences, this is n squared. So maybe you want an attention that only attends just 100 positions before and not the others, or some other restriction. So there are many attention types. There are many types of this feed-forward layer. There are many types of the positional embeddings. Like we made one with an RNN today. There can be many other. So the model when you don't just do it in Colab for experimentation, but in a code base that's used more widely, it becomes parameterized by these different types of things. So I want to show you a little bit the code base that we use for our experiments. And also when you run not in the Colab, but on the servers, we get this tensor board that monitors these things. So I want to give you a quick overview of that. And then I want to show you how to use a pre-trained transformer model. So we'll just load a checkpoint. So you can see how you could use this code base and just translate things. So let's do that for 5 minutes. And then we'll try to add a layer of the transformer to the sequence tasks we were doing before and see, well, they were solved anyway, but maybe instead of the position RNN, we can just have an attention. Maybe it'll work. Let's try this. And then there is like one more question that I'd like to think about. But first, so the transformer model, it is a part of the tensor-to-tensor library. So it lives here in the tensor-to-tensor models transformer, right? That's where you can find it on GitHub. And it's the same code that we use at Google. It's automatically synced all the time. And how does the transformer model look? So it has like encode, which is not much. It kind of, you see, it's just code passing through, right? It calls like some prepare encoder, dropout encoder, whatever. So we need to look at these functions, right? And then decode, it calls whatever, dropout and decoder. And then body, so we separate in our Colab, right? We get the data, and as you notice, there is always like a reshape at the beginning, because the data, like on different problems, it might have different sizes of the vocabularies, different numbers of tokens. Maybe it's an image, maybe it's a sentence. So there is some preparation. It happens in a different function of the model class. There is a model bottom and model top that handles the preparation and the losses later. And the body is just the architecture that happens in the middle. So what does a transformer body do? Well, if it has an input, it builds the encoder with a self-encode. If it doesn't have an input, you were asking, what does it do on language models? Well, it's just a decoder, right? And prepares a decoder, calls self-decode. And then you see if there is some expected attentions, it does some additional loss. So why is it here? Well, in some tasks, for example, when you care about alignment, you care that your attention aligns with something that you have some data about, you might want to train with this additional data, and that's how things get added. And then there is a lot of functions about decoding, because as I said, this model is also used in products, so it needs to be really fast to serve Google customers. So we have greedy inference, fast inference on TPU, a lot of code to speed up inference, to not calculate things, to cache things. We just scroll through all of that. You see fast decode on TPU and fast decode on GPU. And luckily, if you want to make it really fast, then you need to optimize for a certain hardware.
Is it used in Google Translate?
It's used partially. Yes, it's not used for all languages on all servers, but it's used in some parts. Right, encoder. Let's look. Let's look at the encoder. So this is transformer encoder. And what does it get? So it gets encoder input. That's what we understand. That's the X. But then you see there's also something like encoder self-attention bias. What is that? So the problem is the sentences have different length. So to put them into a batch, we have to pad them with zeros to be of the same length. When you're attending, you don't want to attend to the padding. So that's what this matrix ensures. It's a mask matrix to not attend to the padding. Save weights too. We sometimes, for example, to visualize weights, we want to store this tensor. That makes it. Make image summary. So the attention matrix says what attends to what, and sometimes we want to look at it. So that saves the things. So as you see, when the code gets more widely used, it adds all these options. And how does the code looks? Well, here seems to be the main loop for layer in number of layers. Well, we start with the self-attention layer, and it calls this common layers multi-head attention, right? Looks good, but you see, it has a lot of parameters. It has how many key channels, how many value channels, what's the hidden size, what's the number of heads, what's this dropout we will use in attention, what's actually the type of attention, where to save ways. Oh, as you see, when it expands, it adds hyperparameters, and then it's done. Then we do the layer post-process, which is the normalization I told you about. And then there is the feed-forward layer, which, again, has some parameters, like which layer type and so on. So, yeah, but that's the code. I mostly wanted to show you that, yeah, when you look at it, it might look, oh, their architecture was so long, but the code is has 1,000 parameters. Yes, it does, because for different problems, that's what we tune. And it's easier to have one code with parameters, especially when you have automated hyperparameter tuners. So you just give it to the tuner, and then it tries different possibilities. I also wanted to show you, so this is a view of TensorBoard. It's when you train on a server and you start TensorBoard, you get things that look like that. And for example, so you'll get a global step, which says like how many steps per second does this model make. So like 2 steps per second. I don't even know what model this is, but you have different losses. This is some GAN, it's a GAN loss. And then, so we computed accuracy and loss on Evo, but there are many metrics. Maybe you're interested in top 5 accuracy. Maybe you're interested in perplexity. So in the library, what we do is we have a number of metric hooks, and we compute all of them in every eval step. So yeah, so that's how it works. And let's take a look at the multi-head attention. Where is it? Here. So multi-head query, memory, bias, key depth, value depth, output depth. So you see dropout rate, and then a lot of additional parameters. But the ones that have default values, you can usually stick with the default ones. And what does it do? Well, it makes some checks. And then, so compute query key value, right? It's the matrix multiplies which you will make on this query antecedent, meaning x. And then sometimes we already have cached values. That's for fast decoding, so you can ignore all of that. Then we split the query on the number of heads and compute key and values if they were not cached. And well, and then because we have different attention types, the one that we talked about today is the dot product attention, but you can try many different. So this is like the default attention. So the dot product attention queries keys values does what I've shown you. And yep. But as you see, there is a dot product relative v2, local with block, local mask, local unmasked. You know, people are experimenting. And yeah, and that's the function. So if you want just one attention, you can call the dot product attention function. And I'm showing this to you, so if you later want to use some of these functions, you can just import this common attention and use common attention dot product attention. It's often beneficial to use functions that are in a library because sometimes there are subtleties. So the way to do it, you see, it's like here we import from tensor layers, import common attention, and we can call common attention dot product attention, right? So there is Q key V and a bias. And the bias, I think, can be none. So yeah, so you can put none as bias. And then that's the code that I've shown you on the slide. It does the one matmul, softmax, and the other matmul. Okay, so now you know where the code is. And in the Colab, we did the sequence models parts. So how we can run a pre-trained translation transformer model. So then reset the graph, get the problem. So the problem, you can get the list of all problems by calling problems.available. Maybe I will put it here. But this is this English-German translation on WMT with a 32,000 vocabulary. So to like convert text into integers and integers into text, you need this vocabulary file, which is in this Google Cloud storage buckets. So we need to copy it from there. And this is also, if you train your own model, you can copy it to a Google storage. So if your Colab goes away, your checkpoints or your data will still be there. And then feature encoders is the thing that translates from strings to integers and back. So to encode, you get the string, and this thing will tokenize and encode it as integers. And then we need it in this batch shaped, so batch size is 1. And for decoding, it's the other way around. So that already run. And then tensor to tensor has also a library of models, right? So you can set the model name as transformer, and this is a set of hyperparameters that we use for translation, because as you saw in the code, there are a lot of hyperparameters. What kind of attention, what size of the layers, what dropout, whatever, right? You need these parameters to run the model, so we declare them in sets, and then you get the model by calling registry.model, gets all of that. And then we need to download the checkpoint. So the checkpoint is again in Google Cloud, and this thing downloads it from Google Cloud to this virtual machine. And then this is how a translate function works, right? It encodes the inputs, runs model.infer, which is not the training mode, right? This is the one where the graph is not feed forward. It has a scan. It does one thing after the other. And so it restores the parameters. So this is the saver restore, right? It needs a session, and it restores parameters from there. And then it decodes the string. And yeah, it looks like this has already run. And you have a result. So you can, if you want to translate your own sentences, you can give them a try. I said it's quite a good model. You can check if my word is worth anything. Another interesting thing, so this is a bit complicated. I will not go through this code, but you saw that there is a way to save the attention weights, and we have some JavaScript. So in the Colab, you can import JavaScript to make visualizations of the attention heads. So this is the sentence tokenized. These are the tokens, which correspond to integers on input. And this is exactly like the things I've shown you in the talk. So every single color is a different attention heads. Here, because there are 6 layers in this model, so here you choose which layer you want. And if you click on the color, you can choose which. Maybe here you can choose. So there is the encoder attention, encoder decoder attention, and just the decoder decoder attention. So you can choose which one you want, and then you can see what every word is attending to. So this is the, we wanted to see the it, right? So let's see in the input attention, this is it. Oh, or did we want tired? Oh no, we wanted to see it and see whether it attends to the animal or the street. So on this layer, nothing seems to attend there. Maybe on a different layer. Oh, here, yeah. So this is how you can play, right? You can actually see in this way which layers of this model are attending to what. So if you sometimes want to investigate a little bit what this model is doing, especially useful when your model is not doing well, then this is how we look at it. Okay, so that's what I wanted to show you. And now, yeah, let's go back to the programming part, especially to the sequence part. So we made positions with a scan, right? That's what we did in the morning today. That worked very well. How about replacing that with a masked attention layer? So I suggest we use this common attention dot product attention or common attention multi-head attention. But yes, we will need a mask to only attend before. So please go to the GitHub pages of the common attention and the transformer. Figure out which function to use to have the masked attention. And let's replace the scan here by just an attention that attends to the positions before. And let's see if that will work for this sequence task. So yes, and ask questions if you need help. So you can write things like this. So the common attention is already imported in this Colab. If you have the latest version, but. So how is it going? Did you figure out which function do we want to call for the attention? So maybe, do you want to call the multi-head attention or just the dot product attention? I think both are fine, but depending which choice you make. So there is the queries, keys, and values. They will be created, right, by the dense layers. But the question is, what is the bias thing? What will we put in here? Right, it's a decoder attention, so it needs to have this 0-1 matrix to mask it. That needs to go into the bias. Did you figure out how to get it? Well, or we could use, I mean, this is actually, our model is actually not autoregressive, so we don't have to care about it. And if we did, the function would be this one, attention bias lower triangle. That's the function that builds this 0-1 matrix that ensures that it's causal. On the other hand, our sequence model is actually non-autoregressive, so we don't care. So we can actually use none here too. Nevertheless, we'll need the queries, keys, and values, which we create with a single layer from X. So did anyone get to it? We want to replace these things, right? We want to remove this scan and see how replacing the RNN with attention.
Why did you say that it's not autoregressive?
Sorry?
That it's not autoregressive.
Well, this model is not. We did it in the morning, right? There is just one output for one input. It takes the input, processes it and generates the output.
Okay, but if you want to replace the scan function, then the scan function has been generating kind of a vector for our positional embedding, and then using this vector, we were generating another vector. And so
Yes.
And if you wanted to replace it with attention, and I thought it would be like the decoder part when we look at the first generated token, then two generated tokens, three generated tokens, in order to.
Yes. So maybe actually it's not a good idea to replace this scan with attention, right? It will not help us definitely. And it would actually, because it would lose the positioning, it would not work well. So replacing this will not work really well, but what you're saying, it's right. We could make the model autoregressive on the output. So maybe we should try that. How would we make, so we can keep the positions, but instead, here when we are generating the output, right? So before this final layer, we should say H is some autoregressive function, meaning it is some function of H and previous Y. Okay, so that would make it the model autoregressive. Yes, is that a good conclusion? So what function would we use here? So for one, we can say, since we want to use previous y, we would like to shift them by 1. So we can say y shifted we already have a function in the layers. It's called shift right. Just pads a 0 on the left, then shifts everything by 1. So now we can say, oh, but y actually, so y are our targets, but we never embedded them, right? So we should say, this and
T is missing. T is missing in my out.
okay. So we don't want to call it C, like, let's call it ymp. Yeah, that would share parameters. So since both our inputs and outputs are the same, we could share parameters. We could make them different. You know, it's also a hyperparameter in the transformer, of course, as everything. So we have the embedded y. This is the shifted one. So now we can just say, for once, we can add it to x, right? The shifted. So now we have whatever we produced. Oh, sorry, not x. The h together with the shifted vectors. And now we want to do an autoregressive thing, meaning we want to say this, right? So we want this queries, keys, and values, and then gather the attention over the bias. So we'll have the dense layers. We'll have one for queries, one for keys, and one for values. Now, bias, we said that this, we generate like this. And yeah, so does something like this look okay? It looks like now we made our outputs autoregressive based on the shifted part. Yeah, what do you think?
So in this this dot codification should be in the line with the cursor.
Oh, sorry, I think I need to move it up a little bit. It's, yes?
In the line with the cursor.
in.
Common attention is done.
Oh, yeah. Sorry. So what do you think? Does that? Yeah.
Keep it question. So we add this embedded Y to make this model outer. Okay, just confirm.
Yes, yes, because other like autoregressive in this strict sense means it really depends on the previous outputs, and in this case the outputs are Y, right? That's so. In this model, right, I think this is very important to understand. These are our x's, right? There are 10 of them. And these will be our predictions. Well, here are our layers. So this prediction is, what should it depend on, right? If we add the targets, like if we add this position I, this is the target, right?
Okay.
This thing is supposed to predict this. So we cannot add it because then it will never rely on the x, right? It will be 100% correct immediately, but you will never be able to generate anything, right? So this thing has to depend on these things, because we're just adding it pointwise on the same position. So to make it sensible, we need to shift it to the right, right? So we need to actually pad. The shift right is just a pad with a 0 on the left. We could write just TF pad. So does it look reasonable? Apparently it doesn't look too reasonable to the compiler. Oh, unknown activation function. So we messed something up with shapes. So this is actually a very common thing that happens to you, and one reason why many people want a dynamic graph mode for debugging. You get a message like this, and you're like, you know, shape 10 versus 1, so we have now 10 on both axes, which looks not great. But why and what happened? So now you need to scroll a lot to actually see it. And as you see, you scroll through a lot of things.
Saying by Lebec that I never integrate in public.
Oh no, that's no. It's actually not. You know, debugging is not easy, but it's not that hard because we have something of shape 10 by 10. We were doing attention. So we need to start asking ourselves, maybe that's what it gives us back, right? Maybe everything's correct, but we did not look too carefully at it. So these things are the right shape. There is a bias. And probably we're trying to add here something of a wrong shape. So, oh no, it's dot product attention matmul, actually.
I tried setting match to none, which I know Does it succeed? Does it succeed?
Oh, with bias equals none, yeah, let's see.
Yes, but the bias is set to none, then this access to the whole sequence.
Well, but it should succeed in like step number 10, right? It's always good to check. No, not that early. Actually strange that it, yeah, but then it succeeds very dramatically. So what should this bias be actually set to? Oh, I'm not sure if that's the right thing to set. Oh, I understand. So the attention function actually expects it expects things that are three-dimensional. So we used conv2d, right? We added this extra dimension of 1 just to use two-dimensional convolutions, while the functions expect yeah. The functions expect three-dimensional tensors, which makes more sense, you know. Oh, no, it was 4. Oh, batch heads. I see. So this is already made for multi-head attention. So we want one head. So this operation, right, will squeeze this additional dimension we added and add one on a different thing, because this thing, as you can see, already expects a number of heads, right, outside of the batch, while this thing now it runs. So these shape problems are kind of prevalent. They happen a lot. So now we have the right bias. The model is autoregressive now. It still runs, still learns. But, you know, so this thing would run anyway. But let's make it so that we have some benefit from the autoregressivity, right?
The bias is still none. Is it like
Oh, sorry, the bias is still none. that's bad. Uh-huh. So now it's different. It's very good at overfitting because we're only training on sequences of length 10, and instead of learning what we wanted it to learn, it somehow learned to just look at the previous things. So now on the length 20, it's generating something different, right? We can check, is it overfitting? So there are two different things. It can be overfitting or it can be not generalizing, right? Let's try to run it on the same lengths.
Aren't you keeping, is it intentional that you have TF scan kept there in the code?
Yes, because we still need position information. At least, you know, we have it. So let's see now. Now the training and evaluation are of the same length. And yeah, it seems like it's doing really well on things of the same length, but on things of different length, it starts to fall apart, right? So it seems to overfit to the fact that you're just having same things. But the things I wanted to take like maybe 2 more minutes. So this was a deterministic problem, right? But let's make it, you know, let's make it more fun. So one problem is to like do the sequence we had, but in the other case we want to copy and we can do that, right? So half of the times we'll just copy the sequence. The other half of the time we'll want this other sequence. So that's a problem that's not deterministic. And the thing I talked about, so you can see sometimes just copies, sometimes it should be, yeah. So now this is a problem where we would hope that our autoregressive model should fare reasonably. And we'll see if it does. Well, you see, it's progressing more slowly, but it is, right? It's getting accuracy 94, 95, 97, despite the fact that the output is actually random, right? In one case it's this, in the other case it's that. But it's really getting good accuracy here.
It's getting 97 without this positioning. Is it normal?
Yes, well, because in this problem, you are repeating the previous number. So it can just append to the previous thing and put it out.
I mean, but it still needs to know whether you are the odd position or the even position, or maybe understand the question.
So it was not a question, it was a statement that if you comment out the TF scan part, it still works.
Okay, it's a good question for why. I think the attention just compensates for the lack, but we need to figure out how. But one thing that would be maybe nice to check is what if we don't have the attention and don't have the autoregressive part, would it still manage to solve this problem? And no, it still does fairly well. Oh, it's an accuracy on the. So a totally random thing would get 50 here, right? Because we're producing bits. So, and now both identity and like one of the bits is always the same. Yes, this is a bitwise accuracy. That's why since one is the same, then 75% is very trivial. And then the other one, well, half of the time I might guess it right, and they're only 10 long. So, well, it's doing it, so it must be true. We should measure the full sequence accuracy, right? That would be more interesting. Because full sequence accuracy here would be 0, while in the other case, it should be 50%, because it still doesn't know which one it should be. And that's, so I would say, if you have some free time in the afternoon, in the evening, give it a try. Try to figure out why you can remove scan and it still works. Try to figure out what's the sequence accuracy, right? Why is it 88? How comes it's... but clearly, this autoregressive part does help, right? It was 99 with it. So, and I hope you know how to add attention to your models. This is just one layer, but with the multi-head attention function, you can have more, and then you just do a for loop. Thank you. And see you tomorrow for more transformers. Oh, right. So tomorrow I'll talk about universal transformers. But then at the end, at least for those of you who want to submit homeworks, we would like to ask you to think, what would you like to do? So if you have some deep learning task that's keen to your heart, that you really want to solve, tell us tomorrow, and then we can talk together whether it's a good thing for a homework, or whether it's too hard or too easy, or how to modify it to make it a good task. So please think about it, so we can decide tomorrow together what are good homework tasks.